Autonomous vehicles rely on robust perception to navigate safely, especially in challenging weather conditions like rain, fog, or snow. While cameras and LiDAR have become standard sensors, they suffer from reduced reliability under adverse conditions. Enter 4D millimeter wave radar, offering a compelling alternative. Its longer wavelength allows it to penetrate atmospheric particles, maintaining performance when visibility drops. Modern automotive radars don't just detect objects. They measure their radial velocity via the Doppler effect, providing a rich, dynamic signal that enhances object detection. Yet despite these advantages, radar-based perception still lags behind LiDAR-driven methods. Why? Two key challenges stand in the way: the extreme sparsity of radar point clouds, and more critically, the scarcity of annotated radar data. Labeling radar point clouds is labor-intensive, time-consuming, and costly, requiring precise synchronization across sensors and manual effort to annotate each object in 3D space. To bridge this gap, we present 4D-RaDiff, the first latent diffusion framework designed specifically for generating high-fidelity 4D radar point clouds, complete with spatial coordinates, Doppler velocity, and radar cross-section, RCS, values. Unlike prior approaches that convert radar data into images or apply diffusion directly on raw points, our method operates in a learned, regularized latent space. This allows us to preserve the unique characteristics of radar while enabling efficient, controllable generation. Here's how it works. We begin by training a point-based variational autoencoder, VAE, to compress radar point clouds into a structured latent representation. Each point is encoded with its 3D position, Doppler, and RCS, then mapped into a compact, continuous latent space where the geometry and features are preserved. Once trained, the VAE becomes a fixed encoder, and we train a latent diffusion model, LDM, on this latent space. Crucially, we disentangle the generation process into two components: foreground and background points. Foreground points, those within annotated 3D bounding boxes, are generated by conditioning the diffusion model on the box's position, size, yaw, class, and velocity. We use a cross-attention mechanism inspired by layout diffusion, extending it from 2D to 3D to allow fine-grained control over object shape and motion. This ensures that synthetic points not only match the spatial layout, but also exhibit realistic Doppler values based on their motion. Meanwhile, background points, everything outside the bounding boxes, are synthesized using LiDAR point clouds as conditioning input. Why LiDAR? Because it provides a highly accurate, dense representation of the static environment: roads, buildings, trees, and terrain. By conditioning on LiDAR, we capture the complex context of the scene, clutter, noise, and spatial structure, while maintaining radar-specific properties like RCS distribution and Doppler signatures from stationary objects. This separation is key. Foreground points are dynamic, often composed of distinct reflective surfaces. Background points are mostly static, dominated by noise and environmental clutter. Modeling them separately enables us to generate each with high fidelity, tailored to their underlying statistical distributions. Now, why does this matter? Because synthetic data isn't just a theoretical exercise, it's a practical tool for training better perception models. We validate our framework on two real-world datasets, View of Delft, VO-D, and TruckScenes. Both provide synchronized radar, LiDAR, and 3D bounding box annotations. First, we test data augmentation. We use GT sampling, inserting synthetic radar points and their corresponding boxes into training samples. On VO-D, combining real and synthetic data boosts center points MAP by over 7% compared to real-only training. On TruckScenes, where class imbalance is severe, pedestrians and bicycles are rare, the improvement is even more striking. Detection performance for these underrepresented classes increases significantly, with minimal impact on cars. But the real breakthrough comes from pre-training. We train a centerpoint detector entirely on synthetic radar data generated by 4D-RaDiff, no real annotations required. Then we fine-tune on just 10% of the real data. The result? Performance matches, or exceeds, models trained on the full real dataset. In fact, pre-training on 200% synthetic data, followed by fine-tuning on 10% real data, reduces the need for annotated radar data by up to 90%, while achieving comparable or better detection accuracy. This demonstrates a powerful paradigm shift. Synthetic data isn't just a supplement, it can be the foundation. The model learns the fundamental structure of radar perception during pre-training, then adapts to real-world nuances during fine-tuning with minimal labeled data. We also conduct extensive ablation studies. Removing the VAE and applying diffusion directly to raw point clouds leads to poor results: higher chamfer distance, worse Doppler and RCS fidelity. Our latent diffusion approach outperforms even state-of-the-art point-based diffusion models like SPVD, especially in preserving radar-specific features. Of course, limitations remain. Our model generates a fixed number of points, which can cause density mismatches. Partial occlusions aren't modeled, so we sometimes generate foreground points where the real data has none. Also, we don't yet simulate motion trails across multiple radar sweeps, though this could be addressed by incorporating ego motion compensation. Finally, background generation depends on LiDAR, making the method sensor-dependent. Future work could explore conditioning on camera images or semantic maps to increase generalization. In conclusion, 4D-RaDiff represents a major step forward in synthetic radar data generation. It's the first framework to apply latent diffusion to point-based radar representations, generating 4D point clouds with full Doppler and RCS fidelity. By enabling high-quality, scalable data synthesis, it reduces the burden of manual annotation and accelerates the development of robust radar-based perception systems. This isn't just about generating data. It's about enabling autonomy in the real world, where weather, lighting, and visibility are unpredictable. With 4D-RaDiff, we're not just simulating radar. We're building the foundation for safer, more reliable autonomous driving.